Hi, and welcome to the Weak Bases podcast. All right, so the way that you're going to know the difference between a strong base and a weak base is that a strong base is going to have, and you can watch the video on the strong bases, they're going to have an OH in the chemical formula. And it's going to have I'm going to make a little box of them right here. Oops. All right, so our strong bases are going to have OH in their chemical formula, and they also have to have, the OH has to be ionically bonded to a metal cation. So examples would be things like LiOH, but they have to have that OH in the formula. NaOH, KOH. You can even have something like MgOH2. Those are going to be your strong bases. Weak bases are going to come primarily from two sources. They're going to come from amine groups, which are going to be nitrogen groups. An inorganic version of this would be something like NH3. And then you have lots of organic ones. So they're going to have some sort of carbon attached to a nitrogen. And usually that nitrogen comes at the end. You're going to have something like CH3, NH2. That's a weak base. CH3, NH. And I'm trying to show you here, you can have different numbers of hydrogens. They're also going to be amines because it's the nitrogen. Well, so all weak bases are Bronsted-Lowry bases. And if they're Bronsted-Lowry bases, they are proton acceptors. The strong bases over here are Arrhenius bases. They're OH donors. So they give up an OH. These have to accept an H+, and we'll see in a second. When they accept that H+, that generates an OH minor in water, and that's what is why they're considered bases. But it doesn't matter how many of these nitrogens you have. The nitrogen is what does the job of accepting the H+. So you could even have CH3, and there's lots of these, CH3, nitrogen. The other place where you can have weak bases are going to be conjugate bases, and that's covered in another podcast on salts and conjugate acid-base pairs. All right, so why do we consider these weak bases? Why do we consider them bases at all? Let's take ammonia. That's different than ammonium. Okay, so NH3. To all weak bases, you have to add water to show their dissociation. And we're going to think of water as H plus OH minus. And what that NH is going to do, the nitrogen here is going to, it actually has a pair of electrons that are just sitting there, and that's actually what draws in the H+ and forms a bond with it. We'll learn about that more when we talk about bonding. So now you're going to end up with NH4+. Well, what about the rest of water? Well, the rest of water is right here. It's the OH. So the reason why we consider these a base is because they're going to bring up the pH of the water because they generate OH minus. So this would be your weak base. This would be your conjugate acid. All weak bases have a conjugate acid. Let's do another example problem. Actually, before we move to an example problem, I'm going to draw a beaker diagram for this. So remember what it means to be weak. So if something is weak, that means that it does not dissociate completely. So its reaction arrows are going both ways. Most of a weak base will stay in this form right here. It will stay in that form because it's not going to dissociate completely. All right, so we have our beaker diagram. So because it doesn't dissociate completely, we're going to draw two NH3s to show that there are more of them. Now, really, we'd have to draw 1 million of them because there's about 1 million more, but okay, that would take all day. So now we're going to draw one NH4+, one OH minus, and that shows all the species that would exist. Let's do an organic example. So let's take CH3, 2, and H. This is a weak base, okay? And all weak bases, you have to add water because they need a source to steal a hydrogen from. So they're going to take, and remember, all acid-base chemistry that we cover in this class happens in water. So there's always water around. So if this accepts an H plus, your final formula has to have an extra hydrogen and it has to have a +1 charge. And you're left over with OH minus. Okay? So this is your weak base. This is your conjugate acid. All weak bases have a conjugate acid. Before we go on to a practice problem with calculating the pH, I do want to show you what we call the generic form. So if we take, for example, we consider this just B for any base. So let's say you had like NH3. And to any weak base, as be a weak base, you add water to it. It's going to accept an H plus, so it becomes BH plus, and you generate an OH minus. This generic form is incredibly helpful because sometimes these chemical formulas are very long. When you're trying to save time or space on a test, you can always substitute in this for it. So when we do our practice problem, I'm going to use this substitution. So let's take a look. Let's take a look at calculating the pH of 0.02 molar C2H5NH2. That would be ethylamine. All right, so because this is a weak base, we cannot directly know the pH or even the pOH because it's not going to dissociate. We're going to have to take into account the Kb. But before we can take into account that Kb, well, first we have to write the dissociation. So we're going to do C2H5 NH2 plus water. Try to write it as small as possible here. CH5 H3. Now, when I actually do the problems, I'm going to substitute in this as B. Obviously, we still have water. This is going to be your BH plus. H minus, you can't see the OH minus here. Okay? All right. So our KB for this. So why is this a KB and not some other type of K? By definition, a KB must have a OH minus in its numerator. So this would have a OH minus as the products because a K value is always products over reactants. So I'm going to substitute in the generic version of this. So we've got KB equals the concentration of BH plus OH minus over B. All right, so to get values that we can actually plug into this equation, we're going to need an ice chart. So initially, the base is 0.02. And where am I getting this number from? Okay, I'm getting that number from right here. That's in the problem right here, okay? So it is 0.02 molar. All right, and initially, before it dissociates, you have none of both of these. This is going to be minus X because the reaction is going to go this way, right? At first, because all you have is this. It's going to form for every one of these that breaks up that you lose, you're going to get one of these and you're going to generate one of these. This we're going to approximate to 0.02. This is X and this is X. Just like with weak acids, you can approximate the weak bases. You don't need to include that minus X because the value is going to be very, 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 very small. Okay, so we're going to plug in an X for this one, an X for this one, and so we would get X squared, and this is 0.02. And in order to solve this problem, we actually need a Kb value. So we look it up on the chart, and the Kb is equal to 5.6 times 10 to the negative 4. So now we're going to take this and we're going to solve for X. And the reason why we want to solve for X is because that's the value of the OH minus. So we take 5.6 times 4 times 0.02, second square root. Okay, so you're going to get X, which is equal to the OH minus molarity, is equal to 0.0033 molar. And in order to find the pOH of this, because remember all bases you find the pOH first, you take the negative log. So I don't have room to write that. I'm putting negative log in my calculator right now. and I get 2.48. 2.48. And to get the pH, I subtract from 14. So 14 minus my answer is going to be 11.52. I should have been able to subtract that in my head.